Hi everybody, I am Alejandra Barrera and today I want to welcome you to the third class in the series on Introduction to Population Balance Models as a part of the Modeling and Simulation with Partial Differential Equations in Practice course. At this point, you already know the potential of use PVM. You already know about the mathematical framework. Also, the typical phenomena model within the PVM framework. Now, it's time to know how to solve the population balance equation. We are integrating all the pieces together to be able to implement or develop a model. We have seen that the population balance equation is generally an integral differential equation. Therefore, several numerical methods have been proposed and used to solve the population balance equation. Let's start. In an ideal world, the easiest way should be an analytical solution. However, except in certain simplified situations, it is not often that analytical solutions can be found for population balance equation. For example, we can find an exact solutions to agglomeration problems in the absence of particle growth for a variety of simple agglomeration frequency. The applied technique is one of using Laplace transforms. Then, a successful use of population balance equations depends on our ability to solve them numerically, as the analytical solutions are rare. I'm going to list some of the known methods. The method of moments. Even though the method was introduced in 1887, it was not until 1965 when it was used for the first time to address the solution of population balance equation. It is a method of estimation of population parameters in terms of a finite number of some convenient set of functions, such as the Laguerre functions, using Laguerre polynomials. The method of weighted residuals is an approximation technique for solving differential equations. Of course, it has been successfully applied to solve population balance equations as well. Suppose we have a linear differential operator D acting on a function U to produce a function P. We wish to approximate U by a function of U apostrophe, which is a linear combination of basic functions chosen from a linearly independent set. That is this one. Now, when substitute into differential operator D, the result of the operation is not in general P as a function of X, hence an error or residual will exist. The notion in the method of weighted residuals is to force the residual to zero in some average sense over the domain, where the number of wave functions is exactly equal to the number of unknown constants alpha in U apostrophe. The result is a set of n algebraic equations for the unknown constants alpha. There are at least 5 methods of weight residual submethods according to the choices for the WE. These 5 methods are collocation method, subdomain method, least squares method, Galerkin method, method of moments. Next one, Monte Carlo simulation. This method is a sampling technique using random numbers and probability distributions. A simulation algorithm is established by identifying the probability function which governs changes occurring in the system. The algorithm is implemented by generating random numbers satisfying the calculated probability distributions. The probability distribution for the changes in the system are conditional on the state of the system at the instance at which the change is considered. The Monte Carlo simulation method works as follows. Define possible inputs according to some predefined measurement noise level. Then randomly generate inputs according to certain probability distribution over those possible inputs. And then use the inputs to do certain calculation. For instance, add random errors to data and feed model to simulate noise data. And finally, aggregate individual computation results. For example, the average error in parameters estimates. Next one. Around early 90s, the method of discretization of continuous population balance equation emerged as an attractive alternative. When we discretize a model, we are fitting it to bins and reducing the impact of the small fluctuation in the data. We can find some advantage applying this method. For example, integrals become summations, large population become an average, which means that we have to deal with only pivots or representative values for a class, and we can reduce the complexity of the whole equation to a set of ordinary differential equations. Sound familiar in this course, doesn't it? Then, there are several methods for solve under these discretization methods. For instance, those are listed here. As we already saw, we can model different kinds of phenomena based on our system. Therefore, for our population balance expression, some techniques are better for the solution. Here we have a comparison of some phenomena that have been successfully resolved with each technique and the indication when a failure has been reported. Here, aggregation, pure breakage, growth, aggregation and breakage, aggregation and growth, aggregation and nucleation, aggregation, nucleation, breakage, and growth. For our purposes, we are going to focus on the cell average technique. We wish to transform the general continuous population balance equation into a set of ordinary differential equations that can be solved using any standard ordinary differential equation solver. The idea of the cell average technique is to calculate the average properties, which depends on the number of dimensions within the PVM. It means the number of internal coordinates we have. So we want to calculate the average properties of all neighbor particles in a cell or bin and observe the position of average values. It means that we can track the number of particles in each bin. If the average value lies exactly at the node of the cell, which is rarely possible, then we assign all neighbor particles to the node. Otherwise, these neighbor particles must be reassigned to the neighboring nodes, depending upon the position of the average property in the cell. To achieve the assignment of the particles to the corresponding cell, we have to follow some steps. From now on, we are going to see in detail this method using as an example a system where we are going to assume pure breakage as the responsible in the changes in the population under study. As an overview, the main steps are computation of the birth and death rates, computation of the property average, third, birth modification as a key in this method, and substitution in a population balance equation and solution of the set of ordinal differential equations. To get to the end of these steps, we have intermediate stages. First, we have to define the grid. It means the number of beams, or in this jargon, cells, and their range. Keep in mind, it could be not only diameter, but also expressed as volume. We have to express our population balance equation in a discrete way. From a continuous description to a discrete one that can be computed as a set of ordinal differential equations. In this example, pure breakage was assumed. Therefore, our population balance equation is reduced to this initial expression. Then the change in the number density is only due to the birth and death due to the breakage rates at which particles are born and die at a specific time instance per unit of volume, where the output of breakage function B is the probability density function for the formation of daughter particles of size X from the mother particles of size epsilon. The selection function describes the rate at which particles are selected to break. Then, if we use the relation between the continuous number distribution N and the number of particles in cell I, in sub I in capital, and we take into account that the particles are assumed to be concentrated at the representative size, then the number density N, lowercase letter, can be replaced by the Dirac delta representation. The Dirac delta function is a function that is zero everywhere except one point. And at that point, it can be thought of as either undefined or as having an infinite value. Then the particle birth by breakage is the sum over all cells K larger or equal than the cell itself, of the number of particles in that cell Nk times the selection function evaluated in size xk times the integral over the breakage function. For the cell itself, daughter particles in cell I can only be formed out of particles larger than the representative size. Therefore, the breakage function is only integrated over the upper half of the cell. Then we can start with the birth and death terms by calculating the zeroth and first moment. A moment of distribution is a specific quantitative measure of the shape of that distribution. The zeroth moment of the breakage function is equal to the number of fragments, capital N, obtained from the breakage of the mother particle. The first moment is equal to the volume of the original mother particle. As an example, let's consider those particles in a cell X. If we replace the superscript j by 0, then we have the integral of the function n, which is the total number of particles. If we replace j by 1, it becomes the integral of x times n, and we get the total volume. Here, 1, 2, 3, 4, 5, 6, 7 number of particles, each volume. And if we want to calculate the average volume in the cell in this scenario, is straightforward like this. Once we can control the number of particles and we know the volume, we can use this expression to calculate the birth and death rate due to the breakage in each cell. We can calculate the net flux in the cell to get the net volume flux into the cell I. We need to multiply each term with the volume of the resulting particle. And then the average property, the average volume of all neighbor particles is computed by dividing the total volume birth by the total number birth B due to the breakage. Since this method seeks to locate each particle taking into account its properties, relocation is necessary by calculating the expression of modification of birth. Notice here the new terms lambda and h. Let's look at it in a little more detail. Each particle has 4 options to be located or reassigned in the neighboring cells. If the size of the particles is greater than the representative size of the cell, -1. If the size of the particles is less than the mean value of the cell X. If the particle is larger than the representative size of the cell. And finally, if the particle is less than the mean value of the cells +1. If you are wondering what about the death term? Well, since those particles disappear, we don't need to reallocate them. Then is no need to alter the death term since particles are just removed from the grid points and therefore the formulation remains consistent with all moments due to discrete death. Now, substituting the birth and death terms, we can solve the set of ordinary differential equations. And in the case of the Python language, we can use any integration scheme that is available in the SciPy library. Further details of each technique, you can look at this reference. So don't hesitate to contact me if you need something else.